Hi everyone, thank you so much for joining us today. We have a guest speaker session with Gowthami Somepalli. Gowthami is a PhD candidate in Department of Computer Science at University of Maryland, College Park. The focus of her research lies at the intersection of machine learning and computer vision, with the aim of building practical ML systems that are interpretable and robust. Her recent works range from developing novel deep learning architectures and methodologies for diverse domains such as tables, images, and language, to build tools to explain and analyze the success and failure mode of common deep learning models. Before starting her PhD, she worked in industry in various product and engineering roles and received her bachelor's from IIT Madras. She is also a recipient of Kulkarni Fellowship, Amazon Research Fellowship, CVPR Doctoral Consortium Award, and Anne Weil Research Fellowship. Thank you so much for your time and overview.
Uh, Thank you so much for a kind introduction and thank you for inviting me for this presentation. And also, so today I am going to talk about like my the work I have done. I have been doing like for the last 1.5 years. And um, okay, can you guys see my screen fine?
Yes.
All right, sounds good. Before we get started, like I just want to tell you guys, like I would like this session to be as interactive as possible. And if you have any questions, like just feel free to stop me, and or send a message on the chat. Like I'll try to like stop and like try to go into a little bit more details or try to explain this a little bit more. Okay, so. Today, I'm going to talk about my research on understanding memorization in diffusion models. Like we have been using generative models for the last few years, and basically over the course of last 2 years, the models have become really good in terms of generations. Like, so here I give an example of like how far we have progressed. On the left side, we see like the generations from the first GAN paper by Goodfellow et al. And as you can see, like they were doing numbers fine. However, when it comes to like traces or even like the generations on CIFAR data set, like they're barely they're not good at all. Like, and on the right side, like I give an example from last year STXL model, and as you can see, the generations we have come like very far in terms of like the quality of the generations. And however, and we can kind of like attribute this progress to like both data and compute. Here I show a couple of plots like about like how scaling has been done like in terms of diffusion models on the left side, and then some of the LLMs on the right side. We have scaled both in terms of data sets as well as the compute, like how big these models has to be, and like how long we can train each of these models for. Even then, I mean, we have come far, but however, there's still a bunch of issues. I mean, like, are these models ready for deployment? Like, not really, because there are so many issues like safety or compositionality issues. Like, for example, if you go for really complicated prompts, models kind of tend to get confused. And I mean, we all are aware like how these models are not capable of generating like text on images, or they kind of get confused between like the color of the objects or things like that. And one of the issues which I have studied like in detail is memorization. It's one of the quite problematic issues, because it's not just about like the inability of the model. It's also about it brings about some of these ethical issues, like for example, some of these Stable Diffusion has been sued by like bunch of these guys, like by Getty Images and also a bunch of artists. And recently, like there have been like a lot of discussion about how DALI and Midjourney are trained on like copyrighted images, and in fact, like not just about. I mean, even how we got to know about it is because they're literally spitting out like some of the images from the training data. Yeah, it's a very hot topic, and in this talk, like I'll be approaching it from more like a technical perspective, because these models are not like trained when they're trained on such large data sets. Like these models are not supposed to memorize like some of these training examples. And I try to like address that from technical perspective rather than ethical perspective. Of course, these models have to should be trained on images which are sourced ethically. And I do not want to, I mean, I will not be talking about it per se, like I'll be talking about it like, okay, can we solve this issue like from the technical side? Okay, so this is the outline of the talk. Like I'll be presenting like my three papers, like each of them addressing one of these topics. Like first part, like first paper, like I'll be talking about like whether diffusion models memorize. I mean, this is perhaps like a moot point at this point because everybody is aware, like okay, these generative models do memorize from the training data. However, it was not a very known thing like 1 year back, like when I was studying this problem. And so I'll briefly touch upon it, like just to show like how we approached to this problem, about how we went on about like finding memorization and so on. And the second topic is going to be like, let's like now that we found like memorization diffusion models, let's try to understand like why do they memorize it, and we kind of propose like a few strategies of like how we can go on about reducing this memorization. And lastly, the third topic is like about style memorization. So this is one of my recent papers, and the preprint is just out like last month. So we kind of like try to attack this style memorization issue. Like first of all, like style is a very abstract concept, and we tried to formalize it a little bit and try to propose a way to extract style from images, and then went on about like, okay, can we actually detect style memorization in diffusion models? Once again, I want to just like I want to keep the session as interactive as I can. Like, please stop me whenever you have any questions. Okay. Yeah.
Just I wanted to clarify one thing. When we are talking about memorization, does
Mhm.
it mean that memorization of like famous personalities or famous buildings or objects, or memorization of specific images from the training data?
Yeah. So that's a good question. So again, memorization is rather than like a concrete concept. It's more of a spectrum. So if you think about it, like remembering exact characters from Simpsons can be usually thought of like some sort of copying or memorization. However, you can think of it this way, like the model is able to replicate dogs also, right? Like it's also a form of memorization. So where do we draw the line on the scale of memorization? It's like sort of a hard thing. I mean, typically like, but however, in this study, mostly we have thought about like more of a regenerating or regurgitating like one of the images from the training data. That's mostly what I would consider as memorization, at least for like first two topics. However, when it comes to style memorization, like again, these lines are quite blurred, and we can discuss it when I come to that section. Did that answer your question? All right, cool. Okay, let's go on to the first part, like do diffusion models memorize and how to find it. Um, all right. So first of all, like let me kind of briefly touch upon like what do I mean by replication. Again, like memorization, replication, copying. Like I might be using these terms interchangeably, even though there are like slight differences among all these three terms. But I apologize. Okay, so let's say like I have generated this dog image from using a generative model, and then I kind of showed this image, and if I ask like all of you, like if I give this image pair, would you call this like a memorization or a replication? 99% of you would say like no, they're semantically similar, but they're not like perceptually similar, so I would not consider this as a replication. And how about this? Like now, some of you would change your stance. Like, yeah, these two images could be considered as copies because, like, this image is more or less a part of the original image, and this image you would consider as like a collage of this image plus some other image. So, yeah, like maybe this can be considered as a replication. How about this? Like now, more or less, like 100% of you would completely agree with me. Like this could be considered as like a potential replication, even though they're not pixel perfect matches. Like, of course, there are some differences between like the original, I mean, this query image versus this matched image, like in terms of either via augmentations or some sort of like rotations or translations. Yeah, so in our study, like we consider more or less all of these cases as potential applications, and this is the exact verbatim text like we mentioned in the paper. Like we consider a generated image has a replicated content if it contains an object or a background that appears identically in the training image, neglecting minor variations like for example, these pixel level differences and so on. Okay, so and the thing is like now that I define like what I mean by replication, now like the problem arises like first of all like how do we go on about finding this replication, and for that like do we have good feature extractors which are able to like detect this sort of memorization. And there we found we were kind of like there was one issue we faced at the time. Like let's say like we started with a bunch of feature extractors and which are pre-trained models. Like they are trained in like different ways. Like for example, in a self-supervised learning, or directly like trained as classification models, or we have copy detection methods as well. And now, if we want to benchmark all these methods on some standard data sets to pick like one or two good feature extractors to study this problem. However, the challenge we faced is like both the models as well as the benchmarks kind of like tend to focus on this sort of matches, or they're trained with these sort of augmentations during their training time. We did not find like any data set or the feature extractor like that are training on this kind of pairs. So for that, like we kind of created a synthetic data set as to kind of like try to we wanted to benchmark like the existing feature extractors on this task as well, and we wanted to pick out a feature extractor which does well on standard retrieval benchmarks as well as the synthetic task. To carry on like to study our future problem. We created synthetic data set in this simplistic way. So let's say like we started with this original cat image, and so this image, if I remember correctly, it's from Pascal VOC. These images we have like the semantic segmentation masks as well. So we kind of like just picked this cat and copy pasted it on top of like a random image background, and now we consider these two as potential matches, and we want our feature extractor to be able to find these matches. And similarly, what we did is we kind of like blocked or cut off like parts of the original image, and we kind of like outpainted or inpainted using some diffusion models. If you see carefully, like here between this image and the original image, we have only this patch as a match. Rest of it is actually outpainted using a generative model. And now we consider these sort of images also as matches. So this way, like we created like a few variations of a synthetic data set, and then we have like a bunch of 7 retrieval copy detection data sets, and then 3 synthetic data sets, and across 10 different data sets. We kind of benchmarked a bunch of pre-trained backbones, and we used like mean average precision as a metric to figure out like which feature extractor is the best overall across all these benchmarks. And these are some of the results, like aggregate results across all 10 data sets. As you can see, like we benchmarked around like 10 feature extractors, and we found like Dino, Swing Transformer, and SSCD to be best performing across both synthetic and real data sets. Um, Now that like we have a few good feature extractors, now the next step is like before we go on about like studying larger models, like at the time we wanted to even do like a very sanity check, like can diffusion models copy? So for that study, what we did is we actually took like what we wanted to do is we take a diffusion model, overfit like a really small data set, and see like whether the diffusion model is even able to remember like this small subset of data. So for that setup, what we did is we kind of took like a original DDPM model without any kind of conditioning, and we fine-tuned on like a Celibae HQ data set. So we studied 3 cases primarily, like 300 images, 3,000 images, and 30,000 images. And what we did, and these are some of the qualitative results of this study. Let me just take a second to explain what's going on in this figure. So we have 3 blocks of images, and each of the generated images, 3 images are coming from each of these respective diffusion models, and the two for this generated image, we kind of match against the training data. And these are the top two matches using each of the feature extractors. So we have SSAD, Dino, and Swin Transformer, which we shortlisted from the previous set of experiments. So let's look at like 300 image case. Like here, the model is actually able to pixel perfect remember all the details of the original training examples. Like here, this lady is wearing some crown kind of a thingy. Like the model is able to replicate that as well. And I mean, even minor details, the model is able to replicate really well. And then if we move on to like 3000 image case, here the model starts like not memorizing as much anymore. Like for example, in this case, like the background, it did not get it quite right. And similarly, in this image, like the lady's lipstick color has changed and so on. And as we move on to like the model trained on all 30,000 images, now we don't see any exact copies anymore. Because like if, for example, if you take these two guys, like it feels like they are either the same guy, probably photographed on a different day, or maybe these two women could be like related, but they're not exact copies anymore. So that's what we found on like a small scale study. This is some of the qualitative results, and we also did like a quantitative analysis. Like we don't want to just look at like three images and say like, okay, fine, they memorize or they don't memorize. So instead, what we did is, so we have these three trained models, and we took each model and generated like 10,000 images. And yeah, and then now we have like a generate 10,000 generations. And what we do is for each of this generated image, we map it against all the training examples and compute like a dot product similarity. And we kind of take like top one dot product similarity of each generation against all training examples. Now, this gives us a sense of like how much, how close each of this generation is with respect to like the training examples. And we kind of like plotted these similarity scores. Again, like let's focus on like one plot at a time. This plot is for like the model trained on 300 images. And on the we are just plotting the histogram of top one similarities of all the generations with respect to the training data. As you can see, like we have I mean, we have like a lot of mass like distributed on the right side of the histogram, closer to like one or between like zero point 0.8 and 1. That means like all this, most of these generations are either pixel perfect or more or less very, very close to the training data. And here the green plot is just to show like cell similarity within the training data, just to get like some sort of a baseline distribution. When we move from 300 points to 3000 points, the model trained on 3000 points, now this mass slowly starts shifting towards the center. And when it comes to like all 30,000 points, the mass is more or less like aligning with the baseline distribution. What it says is like, as you keep training these diffusion models on like more and more data, like the model tends to not memorize them as much anymore. That says like if you are given like same amount of budget, compute budget, and if you have like more and more training data, like the memorization tends to come down. Uh, is that clear? This is a very important plot. Please tell me if it's not clear, because this kind of forms basis for like rest of few of the slides later on.
Sorry, what was the sim train?
So it's kind of like just a similarity between the training examples themselves. Like we kind of conduct a very similar like exercise within the training data. Like you take each training example and compare it against all the other training examples, just to see like if to give like how some self similarity within the training distribution is.
But you don't compare with the same example, same
No,
training
no,
example.
no, we don't want to compare. Like then the whole of the distribution will be
Exactly.
like
Okay.
one, right? Like so
Yeah.
we don't compare it with itself.
So you're finding the next best match.
Yes.
Okay.
Um, it's I mean it can be equivalent to KL divergence, but it's not exact KL divergence. Um, Okay, there seem to be a few questions. Is this phenomena for only diffusion models or any generative models? This is not specific to diffusion models. And there was like one GAN paper, somebody studied like GANs a couple of years back, I think. They also found like a somewhat similar-ish phenomena on GANs as well. So it's not particularly diffusion models. However, it's quite possible that diffusion models tend to memorize slightly, little bit more than GANs because of the way they are trained. Because we are literally trying to minimize like L2 distance between like the generation and the original image, right? So the extent to which the memorization happens might be slightly higher in diffusion models, but it's present across all generative models. Right. Let's move on. Okay, so at this point, we were starting to think like, okay, fine, maybe if you kind of train on like larger and larger data sets, like models, diffusion models don't tend to memorize. And then there is a question, can we say it is not overfitting in the 10,000 examples? Yeah, it is a form of overfitting. Memorization is a form of overfitting. And I'll probably touch upon it like briefly in one of the later slides. Okay, so all right. So then the next step is like we went and we wanted to study like a Stable Diffusion model, which was like V1.4 at that time, and we kind of repeated like a similar exercise there. We sampled like random 10,000 captions from some of the training examples of the Lion dataset. Lion 6 plus dataset actually, aesthetic 6 plus, which is around 12 million images among approximately 2 billion images the model is trained on, which is even, we are literally comparing the generations against a subset of the training data. And then we kind of generated like 10,000 images. Yeah, and to our surprise, like around 1.88% of the generated images turned out to be potential copies. Let me give you a sense on like how good this number is. First of all, like, so the thing is like 1.88% can look like a very trivial number to a lot of us people. However, when you look at the scale of diffusion model generations, like, like imagine they in the last 1 year itself, like maybe there are millions of stable diffusion generated images out there in the world. So when you look at a massive scale, like 1.88% is not a very trivial number. However, since we have conducted the study in like a smaller setting, we wanted to just understand like, okay, fine, what are the problems with this number itself? And I'll try to give like few examples to give a sense of like how good this number could be. So let's look at the argument, like, is this a lower bound of this number? Can this number be even higher if we study this over a large data set? Because it turns out like we missed some of the matches. So this scream image like was generated. And in fact, like when we compared against like aesthetic 6 plus data set, like this is the top match we could find. However, like clearly this image is very close to the original screen painting, but we were not able to match it because this image was not present in like aesthetic 6 plus data set. However, it was present in aesthetics 5 plus data set, which was used in like latest stages of training of SD 1.4. So these sort of examples might say like, okay, maybe this number is a lower bound. However, the thing is like we only analyze like a few captions. However, as you keep increasing the captions, like the memorization number might not scale like linearly. So yeah, that could be like an argument against it. And the second argument is like, is this an upper bound? Like, is this the maximum level of memorization we could find? Because we have sampled the captions from the training data itself. That's another set of argument. However, there are like a very few interesting examples where even though the caption is like you kind of like give the model a caption and it will generate an image, and then it gets matched to like a completely different image with a completely different caption. And this is one such example. Like we generated this image with this caption, Hill Country Castle by Art Del Angel or something like that. And if you see closely, like, okay, there is some castle thingy like in the painting. and we kind of matched it against like some the training data, and this is the image the model matched to. We were able to match to, and as you can see, like, and this is the caption for this particular training example. And if you look closely, like, there is not even a single word that overlaps between like the caption used for generation and the original caption. So that kind of says like, okay, fine, like maybe if you source caption, don't have to source caption from training data. Even if somebody is like sitting and writing 10,000 captions, it's quite possible we will get this level of memorization with this diffusion model. And there are few other, again, this is another case where like the background is the same, and the case designs are changing, and we get like no word overlap. And there are like, again, the cases in between where a single word kind of overlaps. Even a single word can elicit memorization. So for example, this is the generated image and this is the original image. And as you can see, like the word that overlaps is this word bloodborne, which seems to be the key word here. And as long as you use the word bloodborne and say like whatever you want for the rest of the caption, the model tends to like, it elicits like this memorization behavior. And similarly, like there are a few interesting cases we actually accidentally came across. This one particularly, like you just use the phrase like canvas wall art print, and you add some random text for the rest of the caption, like say like a painting of a garden, or starry night, or a clock, or something like that. Or in a non-trivial percentage of the cases, we found like the model produces this couch with this blanket, these two particular blankets. In some of the cases, even there are like some of the interesting cases where the color of the blanket changes too. And however, like we found around 20% of the times, like we were able to elicit this particular sofa arrangement, like whenever we use this phrase like canvas wall art print. Similarly, like whenever we use the phrase like the great wave, it kind of brings out this wave behavior, like which was kind of famous from this painting by Katsushiki Hokusai. So these are some of the cases where like you don't need like the full caption to elicit the memorization behavior. Even part of the caption can bring it up. So yeah, like so this kind of says like, okay, this is not, this number 1.88 is not necessarily an upper bound of memorization as well. So maybe like it's somewhere in between. Like so it's kind of we need like further studies, like a large scale studies, like maybe we need to compare like memorizations across like millions of generations, and especially like with this caption sourced against humans, to get like a best estimate of memorization in any given diffusion model. Okay, for the question, what was the compute power on which you ran these experiments? Did you analyze on a subset because of compute constraints? Yeah, so this is very true. We first of all like could not even host like the whole ion 2 billion data set in our cluster at that time. And also like we were kind of doing only 10,000 generations again, like because of limited budget we have in terms of compute. All right. I mean, like, I really wish like Stable Diffusion, Stability guys, they themselves should do this study in like large scale and kind of give some sort of certificates about the memorization or something like that. Okay. So the next um, in fact, like for the second paper, we kind of expanded this search space by a little bit. Instead of looking only at the aesthetic 6 plus 12 million images, like we kind of looked at like chunks of the larger subset, like 2 billion images. And again, like this time, instead of sourcing the captions from the training data, what we did is we actually sourced the captions from user-generated captions. There is this data set, Stable Diffusion prompts. I think like somebody scraped them off the Discord channel of Stability, if I remember correctly. And there was like this huge data set of prompts like created by real humans. So what we did is we kind of took like a subset of those prompts, generated images, and compared them against like splits of chunks of like the whole training data on which Stable Diffusion 2.1 was trained on. And even there, we found like a lot of cases of memorization. For example, like this moon landing picture. In fact, is very similar to the original moon landing picture. And in fact, like this image is owned by Getty Images, and which was again like part of the lawsuit and so on. So similarly, like we kind of we also see like the SC 2.1 remembering some of these copyrighted characters or video game posters and so on. I mean, this kind of like adds evidence to our previous study that like yeah, the replication exists in the real world and it could be like problematic. After the like all of this, like what we felt is there are mainly two cases of two reasons why the model could be memorizing. And at the time, everybody was like, okay, yeah, there is like a lot of training data duplication, and that was the only reason like why the models are memorizing. However, we kind of from that couch example or from that bloodborne example, in fact, like we found that we felt that like maybe text conditioning also could be playing a role in memorization, because like at the end of the day, like the text conditioning model clip itself is trained on a lot of data, and there could be like memorization within clip itself too. So we wanted to study both these factors in isolation and together, and that kind of led to my second paper, which I published in Neurex last year. Yeah, that brings us to the second part. Why do diffusion models memorize and how to mitigate it? I'll take a minute here to see if there are any questions. Feel free to. I guess not. All right, let's go to the second part. Okay. To conduct this study, like this is we have to train a lot of diffusion models by kind of varying some of these conditions. Again, like with our limited compute budget we have here, we could only train like a smaller diffusion models. So we kind of like reduce our search space to a few parameters and try to study that problem. And so for this paper, like mostly we kind of took the stable diffusion pre-train checkpoint like ST 2.1, and also like we kind of looked at like smaller subsets of data. We took this randomly sampled like 10,000 images from Lion 2 billion dataset. And there is this ImageNet dataset which is curated by Fast AI folks, like where they just took like 10 different classes from training set of ImageNet. So both of these subsets of data account for like around 10,000 images, and then so what we did is we kind of like trained a lots and lots of diffusion models, smaller diffusion models on these 10,000 images by changing like some of the parameters, and we kind of how to okay, like to quantify the memorization, we kind of conducted a very similar analysis, like I mentioned before, where we train a diffusion model first, and we kind of like sample like some n number of generations from this diffusion model, and we compare it against like the whole training data, and then we end up with like these histograms of similarity scores. Uh, yeah. So before we move ahead, like the one problem with this is like it's very hard to like just, let's say like I'm doing an ablation of like a certain parameter, and then we'll have this bunch of these histograms, and it'll just be so cluttered, and it will be very hard to understand. Like if I just put like a bunch of histograms within the plot and say like, okay, fine, this is how the memorization is changing. So to kind of like make this study a little bit more tractable, what we did is we kind of wanted to condense this whole plot, which represents the memorization behavior within the diffusion model. We kind of wanted to condense it into like a single number. And how do we go about like converting this into a single number? So we can take a mean, or we can take like median, or some sort of central metrics. However, one issue with these centralized metrics is like they don't really represent the memorization, because memorization is typically like lives in the right tail of this distribution, because like we noticed like from our previous studies, like typically similarity scores greater than like a zero 0.5, those are the memorized images. And so that's why we kind of did like a quick ablation on some of this right tail metrics, like maybe we take like 99 percentile, 95 percentile, 90 percentile, and so on. And we kind of did like a quick ablation, and we found like around 95 percentile seems to be like a good indicator of memorization. So we kind of validated it both qualitatively as well as quantitatively. So from now on, whenever I say like similarity score, like it's not just the distribution, it's 95 percentile of this distribution. And that way, like we condensed it into like a single number. Okay. So now the next question is, like I mentioned, like we wanted to study two factors. First one is data duplication. To emulate this data duplication scenario, this is what we did. Like, so we have these 10,000 training examples, and what we took like 5% of those training examples, and we kind of repeat them n number of times. So which is controlled by this x-axis. Like this x-axis essentially tells us like how much a small subset of the training data is repeated, and rest of the examples are present only once. But however, this small fraction of the examples are repeated a number of times. So this kind of emulates somewhat real world scenario where not all examples are repeated a lot, but a small fraction of the examples are repeated a lot. And then this is what we did. Like again, we kind of train diffusion models for all of these cases where each dot literally represents like a single diffusion model. And we computed like similarity scores for each of these diffusion, for each of these models. And clearly, like according to our intuition, as well as the public's intuition, as we keep increasing the amount of training data and repetition of some of the examples in the training data, the similarity scores are going up and up. That says like, okay, yes, memorization kind of increases as you keep increasing the repetitions of examples in the training data. And we also like looked at like how the data repetition affects the quality of the generation. So for that, like we computed FID score. I mean, FID is sort of a problematic metric, to be honest. However, like again, like evaluations are a problem in generative models right now. And yeah, FID is the best we got at the time. Okay, so as you can see, like even the generation FID scores are also going up as you keep increasing the data duplication in the training time. So it kind of says like the mod's not just memorized, like in fact, like the quality of the generation deteriorate as you keep increasing as the data duplication increases in the training set. Okay, the next thing is we wanted to study the effect of text conditioning. So for that, like we have a couple of hypotheses. Like first one is we kind of felt, at least like from our qualitative studies, like memorization tends to be higher for those captions which are hyperplexity. Hyperplexity means like those captions with very unique keywords. Like for example, bloodborne is a unique keyword. Like you don't typically hear this word in daily life, right? Like I mean, if you take like a lot of text, you are more likely to see a beautiful sunset compared to bloodborne. So these are all hyperplexity captions. So we felt like hyperplexity captions tend to elicit memorization and diffusion models, and that was the first hypothesis. And the second hypothesis was like it's not just the image duplication that is responsible for this memorization behavior. You have to repeat both image and captions together. That's when the memorization is elicited compared to just image duplication. So these are the two hypotheses we had, and again we kind of conducted a bunch of smaller experiments. In the interest of time, I will not go into like hyperplexity caption experiment. Check out my paper if you are curious about it. Like, and we actually found evidence that it is in fact true that hyperplexity captions can elicit more memorization. But so let's just jump on the second hypothesis. So again, this is one of the very important plots. Let me take a second to explain what's happening here. So in this case, like the blue color plot. Okay, so this pink color plot is in fact like exact same plot we have seen before. The one I have shown like a couple of slides back, where we are kind of on the x-axis, we are repeating these examples again and again a number of times. However, this blue plot is slightly different in the sense. So in this case, what happened? What we did is, let's say like I have an image and I want to repeat it 5 times. So I repeat the image 5 times. However, I don't repeat the associated caption 5 times. What we did is we kind of created synthetic captions for this particular image, either via using like captioning models or rephrasing and so on. So every time this image repeats, it is associated with a different caption. So that way, like we are repeating only images, but not the caption. So that's why I called it like just the image duplication. However, in this red plot case, like we are repeating like image and caption together are repeated 5 times. So turns out when you for the second case, like where we are repeating only the images but not the captions, surprisingly the memorization is not going up. It was in fact like slightly going down. So turns out like just by breaking this correspondence between the images and captions itself, we can make the model forget or not memorize the training data. uh, yeah, that was kind of like a surprising result for like a lot of people, and that kind of forms basis for like some of the mitigation strategies we propose like later on. Any questions here? Uh, okay, I guess not. All right, cool. Okay, so we kind of after that, like we again, like I was kind of looking at these generations and see what's going on, and what I found is like even for the models which where there is no replication in the training data, we found like a very small fraction of images. The model is still able to memorize them, and I was looking at like what are these examples. Turns out like very simple examples, the model can easily remember them, even though it's not repeated a lot of times in the training data. However, it is capable of like memorizing simple examples like this bow tie here. And in fact, like then we try to understand is it like a population level behavior, and turns out it is. Here we kind of try to see like if there is any correlation between like the memorization versus the image complexity itself. Like we kind of looked at like a few image complexity metrics, either in terms of the compression, like JPEG compression, or entropy in terms of like the histogram of pixels and so on. And turns out there is a relationship. So the model, these models are capable of remembering simple images, even though there is no replication during the training time. Yeah. Okay. So based on all of this, like there are a few interventions we proposed. Um, okay, this seems to be a question. Duplication is nothing but having a reweighting loss. It is equivalent to training only smaller data set. Yeah, this is kind of true. So I mean, like it's nothing but having a reweighting loss, training only smaller data without duplication. Uh, can you unmute yourself and maybe mention this? I'm not very clear. It's not very clear for me.
Yeah, yeah. In this case, the duplication is nothing but suppose if you have 5 data points and then you have
Mhm.
duplicated into like 20 data points,
Yeah.
right? That means you're inherently training with 5 data points, and then the loss would nothing but be 4 times of the given loss or
It's not
something like that.
that exactly because we are not repeating like the whole training data 5 times. We are repeating only small portion of the training data 5 times.
Uh, okay, got it. But that still is nothing but reweighting those
It,
five
it,
data
it,
points.
yeah, I agree with you. So that is exactly what happens in Lion dataset also. Like there was another concurrent paper from Google where they had like this very interesting plot where they showed like some of the examples are repeated like around 10,000 times. However, some of the points are not repeated at all. So that's how real world data sets are. Like a small fraction of the data could be repeated a lot of times. So we wanted to kind of emulate that behavior with this partial data set duplication.
Yeah, I get it. Thank you.
Okay. Cool. So based on whatever we have seen so far, these are few ways we propose to mitigate memorization. Again, like all of this are kind of text-based interventions because we found there is indeed like the text conditioning plays a major role for eliciting this sort of memorization. And so like there are few training time interventions and a few inference time interventions I show here. We kind of tried a few more cases like in the paper. In the interest of time, I don't want to go into them. Like one thing I really want to highlight is this particular intervention where instead of using like one caption for each image, like when you are training, if you're doing multi-epoch training, try to kind of have multiple captions for each image. Like instead of a single caption per image, maybe just rephrase the caption or something like that. So this kind of helps to break like one-to-one correspondence between between the image and certain keywords in the text. And similarly, we have some noise-based augmentation, like interventions, like for inference time. Like for example, like maybe you already have like a pre-trained diffusion model, and you want it to like not memorize certain stuff. I mean, you don't want it to produce like some of the memorized images. So the easiest way you can do is like perhaps add a little bit of noise to your text embedding. That kind of shifts it from this high likelihood image to like slightly lower likelihood image. You can just maybe like add a little bit noise to the caption itself. Again, like that breaks the one-to-one correspondence. However, these inference time strategies are not very robust. They kind of sometimes, like depending on the word or number you add, like it might change the meaning of the caption itself. So yeah, again, again, a study not something to be deployed in the um, in the world yet. Okay, so let's look at like few qualitative results from one of these mitigation strategies, which I think really works well. This multiple caption strategy. So here, what's going on is for this case, like the second row, what we did is again we repeat the same formula. We have a small subset of the training data which is repeated a lot, and then we kind of train the diffusion model, and these are some of the generations from that particular diffusion model. And as you can see, this model is more or less remembering some of the training examples pixel perfect, more or less. And then the last row is a diffusion model which is trained with this multiple caption strategy. So again, what it means is like each image has not just one caption but 20 captions associated with it. And during training time, during training time, like you take an image under text pairs, right? The text will be randomly sampled from one of these 20 captions. So it turns out the memorization is really low in this model. As you can see, the the semantics of the text are not changing. Like the model is still producing this lamp, or it is still producing this green color eyeshadow, I guess. But the generations are quite different from the training data. And what we found is okay, I'll come back to it. And so these are some of the inference time strategies. So the first row shows a few of the examples the Stable Diffusion 2.1 has memorized. And then these are the generations, just by repeating some of the prompts, like we were able to replicate the training examples. And what we did is, again, we took those prompts, we slightly modified them either by adding like a random number, and it led to like completely different generations. For example, I think this one original prompt was like wall view 001 or something like that, and here the new prompt becomes something like wall view 00105 or something like that. Very simple modification, and as you can see, it led to like a completely different generation. So this way, like it's very easy to that just means like it's just one-to-one correspondence between this particular prompt. And similarly, like in this Anne Graham Smith, like which all of you have seen all over the Twitter, like Google. This example is actually from Google's paper, and all I had to do is like I don't exactly remember what we changed, but a very minor modification in the prompt, and the model does not reproduce this image anymore. So yeah, all we had to do is like just break this image text correspondence. And these are some of the quantitative results. And this MC is the multiple caption strategy, like where you train with not just single caption, but multiple captions. And here, as you can see, like these are the numbers, memorization scores without any intervention, and these are the memorization scores with intervention. And clearly, like the model is memorizing less and less. And one interesting thing is we actually computed like FID scores for all of these models also. Like you can check out the paper for it. And in fact, like this MC, when the model trained with this multiple caption strategy had like lower FID scores. That means like the generations are in fact like slightly better compared to like the models trained in an original way. So yeah, this strategy seems to be like interesting and seem to be working. And these are few of the take-home messages like from those two papers. Like first of all, like training data deduplication can solve most of the problems. However, like actually, like I mean, in fact, like everybody thinks like this is the only thing that they have to solve. And in fact, in Stable Diffusion 2.1, they have performed like a deduplication in the training time. However, the memorization still exists because there are two reasons. First one is they have removed the exact duplicates. That, for example, like if a particular instance of an image is repeated a number of times, that's gone. However, the not exact duplicates, like the images I have shown before, like the canvas wallet print, where the sofa is there, is repeated again and again. However, the wallet is changing again and again. And when you kind of use like similarity metrics like clip, these partial matched images are not given high similarity scores. So because of that, they were not able to remove those examples. And that's why, in fact, like the repetition of, I mean, you can elicit this canvas wallet print memorization more in Stable Diffusion 2.1 compared to 1.4. And so that's why like SSCD is a really good metric. And in fact, like I was working with like stability folks, and for for Stable Diffusion 3, in fact, they used SSCD to perform deduplication. And yeah, like and I guess like they kind of accounted for the partial duplication in the training data as well. And the second thing is like this one-to-one correspondence between like certain keywords and particular styles or particular faces. Like for example, you can see like a lot of variations of Starry Night, like either in form of t-shirts or mugs or like wallet or things like that. So that sort of replication is not accounted for yet, and I think like it's still an open problem. And yeah, like maybe somebody will write a paper about it. Okay, cool. All right. So that kind of concludes my first two parts. How am I doing on time? Okay, okay. I'm very late. So any questions so far? I'll quickly go over my third paper. Otherwise, have you considered including multiple images with the same caption? Yes, we did not try this. This is actually a very good question. We didn't include this because of one reason. We felt like the model might not actually be able to learn this because at the end of the day, like you need some sort of alignment between the image as well as the caption. I cannot just, but we should have done this. Like it's a good question. Like I'll try to like get an answer for this for the next talk. I guess like I could have just taken like two different sunset images and could have like the same caption for both of them. Yeah. But my intuition would be like the memorization will be low there also. Uh, Okay, cool. Any other questions? can alignment techniques such as DPO help in removing memorization? So, I mean, like, how do you plan to do DPO here, though? Like, that raises a question. So, I mean, like, for DPO, first of all, like, we need pairs, or some sort of feedback, right? Like, do you have any thoughts about it, Ahmed?
I actually just skimmed over the diffusion DPO paper, which was by Salesforce. So I just had an idea, like maybe if there are some specific keywords
Hmm.
against which we have those specific images from training data set
Yeah,
generated. So
yeah,
if we have that data set and we can
yeah.
create an accepted and rejected kind of pair synthetically and then use DPO to train or fine tune that model, and that might help.
Yeah, yeah, that's a great idea. Honestly, that's quite possible. Like for example, like let's say Super Mario is you don't want to create Super Mario in your generation, so you can use like original Super Mario image as like the negative example, or and you can use something like I don't know, some generic Italian plumber looking image as like the positive image. And yeah, of course, you can move the models away from the original concepts. And that kind of can alleviate some of the copyright issues. That's definitely like a potential direction, like to remove memorization. Good thought. If somebody wants to do it with me, am happy to collaborate. Okay. And all right, okay, let's do this quickly. Style memorization. Honestly, this is a new paper, and this is what I'm very excited about this, because this is a very new direction and a very underexplored direction, in my opinion. So first of all, like in our first paper, we have this plot. Like we kind of barely talked about it. What we did is we took like some 20 famous paintings, and we kind of checked like, okay, the Stable Diffusion 1.4 actually memorize some of these famous paintings. Excuse me. So here in this plot, like I show a few of these generations, and on the top row, like we see the generation, and the bottom row is like the top match for each of these generations. And as you can see, like some paintings, like Starry Night or The Kiss by okay, I forget the painter. Anyway, some of these paintings are like the model kind of pixel perfect memorizes, not pixel perfect, like it memorizes both content and style. However, there are some artists like it keeps diverging away, like the model does not memorize the painting anymore. For example, this Mucha, like he's an Art Nouveau painter, and he has like he predominantly painted women with like this flourishes and stuff. So the model is actually able to remember the uh, underlying style. However, it did not memorize like the exact images. So this kind of gave us a spectrum. So the model on the left side we have like the model memorizing the whole paintings, and on the right side we have some of these paintings like where the model is able to like extract style. However, it could not memorize the exact contents. So that kind of led us to think about like, okay, fine, how do we approach studying the style problem? And for this paper, like this is what we define as a style. Again, style is like a very abstract concept and it's hard to quantify. So we tried in this paper. So it says like it's somewhat of a global characteristic where it can encompass various elements like color usage or brush stroke techniques, composition, and perspective. This is what we try to define as style in our paper. Okay, so first of all, like then that kind of brings us like two major challenges with studying this problem. The first one is like how do you even extract style, and the second thing is like how do you evaluate? Like let's say like you've somehow found like a feature extractor to extract style. And then how do you evaluate the quality of this feature extractor? So that kind of led us to look at this. Yeah, so and then so I mean we literally took a page from the previous paper playbook where we were kind of benchmarking a bunch of feature extractors against a bunch of existing data sets. However, this kind of brings a one challenge. In most of the feature extractors, like let's say like a bunch of these super self-supervised models, they kind of like try to match, like let's say this we have this query image, and then they kind of try to match content rather than style. So they kind of bring, for example, Sinclair has like this color filters. It kind of tries to bring together the features of both of these images for any feature extractor. However, like Van Gogh is famous for his blue and yellow hues. Like that, we literally lost like a style aspect. Like if for this feature extractor, and similarly and other things are like you kind of have crop and so on. So basically, like they kind of try to match like content primarily, but not necessarily always style. However, we in our like let's say this speech style extractor, we want to be able to match to this image as well, like the Starry Night, because the strokes and color patterns also we want to capture. The two images might not have same subject at all. They can be completely different subjects. However, the underlying aspects of style should be the similar. So we did not find any feature extractor, first of all, studying this problem. So we kind of decided, okay, fine, we'll propose our own feature extractor if under current extractors are not good enough. That kind of led us to propose this technique. Basically, it's just a way of extracting features from images, and we called it contrastive style descriptors. And primarily, it has two contributions. First one is it is also again like a type of a self-supervised learning model, except in along with the self-supervised learning loss, we also had like some sort of multi-label contrastive loss. And what do I mean by that is so we kind of made an assumption maybe an artist kind of tends to maintain the style across all their paintings. So what we will do is we will try to match all the images of Van Gogh together. Even if the subject is different, like maybe there is a woman in one painting and maybe there is a table and bed in another painting, even then those two images should be closer to each other. So that's our main loss function in this in our model. And the second thing is we also wanted to use self-supervised learning loss, but we did not want to use photometric augmentations like blur or color jitter, because these kind of augmentations kind of remove important style elements which we want to actually capture in our model. Yeah, and then the second contribution is the data set. So we needed to create like this labels, right? We wanted to bring together all the Van Gogh paintings together. We want all the features of Van Gogh paintings to be closer to each other. So for that, we kind of curated a data set out of Lion 6 plus, again, which is 12 million images, out of which what we did is we kind of curated a bunch of style tags, around 3,840 style tags from this database called Clip Interrogator, which has a bunch of keywords. And we kind of mapped them against the captions of all these Lion images. And we ended up with like around 500,000 images. And we also did like a lot of cleanup. Like honestly, a lot of work went into curation of this data, where we were trying to remove the duplicated images, because we don't want the model to over-index on like certain type of paintings because they're repeated a lot. So, and secondly, we also don't want to represent certain tags. Like for example, word like painting, it's sort of useless keyword. We want to keep important keywords like, for example, synthwave or impressionism, which kind of indicate actually an art style. However, word like photo, painting, portrait, these don't convey like a lot of information. So we kind of did away with those tags as well. And so ended up with like some 500,000 image data set. And then we just trained the feature extractor. And the second step is okay, now that we have a feature extractor, we have to compare it on certain benchmarks, right? So for that, we curated two benchmarks, and first one is the WikiArt, so which is like again art data set, which has around 800,000 images against like 1,000 artists. So we kind of set it like a retrieval problem. So we have a small subset of query images and a huge database of rest of the paintings. And what we do is for any given image, we want the model to be able to match it to the correct artist in the database. And we treat it as like a retrieval problem. So the top one accuracy for this problem is actually like the chance probability is around 0.09%, which is very, very small. So unless I mean, if you're doing a random feature extractor, you should be getting like accuracies of 0.09. And the second benchmark we evaluated the feature extractors on is this domain net, and domain net is in fact like a famous data set for domain adaptation. In fact, like we framed it as an opposite problem. Like in domain adaptation, you want, for example, in this case, like you want this grape image and this grape image to have similar features. However, in our case, we want to retrieve style. We don't care about content, right? Like, so that means like all these clip arts should have similar representation, even though their objects are different. This is actually like a little bit of a golden benchmark in my opinion, because here some humans have actually curated them as like, okay, fine, all of these are clip arts, all of these are real images, and so on. And however, this problem is slightly not slightly trivial in the sense like you have only 5 random classes you can assign each image into, so the chance probability is around 20%. Okay, so along with our model, like we also evaluated on both these data sets, we evaluated a bunch of feature extractors again. So all of these are vision feature extractors primarily, and clip. Clip is another feature extractor where which is not primarily vision, right? Like in clips, we're actually in fact like comparing it against language. So that makes clip actually a very good candidate and competitor for our model, because clip has semantic sense to it, not just the perceptual sense. Yeah, we have some numbers. Okay, let's just jump to our numbers. Okay, so turns out like we kind of compared against another model called GDA, which came out of Adobe, like doing a somewhat of a similar study. And turns out like our model kind of did really well compared to definitely a lot better compared to the Adobe model, and did like a little bit better compared to Clip, because Clip is a very strong contender already. And yeah, these are some of the numbers. And okay, so after that, like we conducted a small error analysis on like, okay, well, is there any pattern to the mistakes our model is making? And so in WikiArt, along with the name of the painters, like we also have like art moments. So for example, like along with the painter, all these some expert has kind of categorized them into a particular art moment, like cubism or pop art or things like that. And as you can see, like most of the errors are like concentrated on the diagonal. That means like the model is actually able to predict the art moment, right? However, it's not able to get the artist exactly. So that could be because like I mean, there is this one particular example where the model is getting confused between Claude Monet and Alfred Sisley, and both of these guys are kind of impressionist painters, and and they also paint like landscapes. So maybe for a lay human, it's equally hard to actually predict the right artist. So that kind of shows like, okay, the feature extractor is sort of powerful, but not too powerful that it can disambiguate like artist level too. Okay, so after this, like we kind of conducted a study on the stable diffusion. I'll quickly go over it. So here, like we created few images from stable diffusion on the first on the first row, these are the top 1 matches from database images. And as you can see, like our feature extractor is getting like the artist right, and also it's not focusing on the content. That's the most important thing I want to show here, because as you can see, like clip, for example, in this dog image, like this is a dog in the style of Van Gogh, and our model literally mapped to like some random painting of Van Gogh, even though there is no dog in this image. However, the clip tried to prioritize both dog as well as Van Gogh here, and yeah, it got it right this time. However, like for example, in this case, like the clip prioritized dog over the style of an artist. However, our models prioritized artists, even though there is a woman in this picture, it got the artist right. So this kind of shows like our feature extractor was slightly better, like in terms of extracting style compared to clip. Okay, so yeah, these are a few examples where we kind of created the generations using like a real user prompts, and yeah, we are kind of able to match it well in terms of an artist. Okay, so this is an interesting study. So what we did is like, okay, fine. Now we have like a good feature extractor, and now we want to do like, can we say anything about the artist memorization in some of these models? For example, like this study was conducted on Stable Diffusion 2.1, and it's very very simple. So what we do is curate in the study. We took like around 96 artists and collected a bunch of paintings from each of these artists, like their real paintings. And similarly, we kind of created a bunch of images in style of these particular artists as well. Now we have like two pairs of images, one original and one generated. And C, let's say C is our feature extractor. And what we did is we kind of extracted representations for all the original paintings and just averaged them. Now this gives us a prototypical representation of original paintings. And we did the similar exercise with the generated images as well. Just extract the representations for all the generated images using our feature extractor and average it. So now that gives us prototypical representation for the generated paintings. And now we just do a dot product similarity between these two. So this kind of tells us like how similar the original prototypical representation compared to like generated prototypical representation for a given artist in this particular model. And we kind of did like I mean by just by changing the prompt, like we can get like different types of generations, right? Like so x-axis has like a general prompt, while y-axis has like a prompt which says like constrained to like a woman in it. So, and what it shows is there are a bunch of artists on the top right corner where like the original representation and the generated representation are very close to each other. That says like the model is actually able to capture this artist style really well. And on the lower left, like we have a bunch of artists like where the generations and the like original representation seem to be very, and the similarity seems to be really low. And then what we did is I actually went one by one, like looked at all these 96 artists, and this is what we found. Just to show like I'm showing like a case of 6 different artists here. Like Leonid Ofrimov. So these are some of the real paintings, and these are generations from different diffusion models. Like looked at SD 2.1, 1.4, and Midjourney. And like whatever I have explained before, like just this number represents the dot product similarity between this particular painting and the prototypical paintings of the original artist. And as you can see, like higher similarities show like, okay, fine, the style is actually transferred. However, there are some artists where the style is not transferred, surprisingly, in HD 2.1. And these guys are the ones on the lower left corner of the previous plot. And as you can see, like, for example, Greg Rutowski is one of the very famously used artists in prompts by all the HD Stable Diffusion artists. Like as you can see, like Midjourney is actually able to create some image similar in style, and we got like a high similarity score. And similarly, SD 1.4 also was able to generate this guy. However, like SD 2.1, we have like really low similarity scores. So, and we have seen this case with like these two artists as well, like Ruangia as well as Amano. And then what we found is, turns out Greg Rutowski has been removed from Stable Diffusion 2.1. He's literally like opted out, and Stable Diffusion 2.1 was not trained on his images. So it turns out like our study, I mean, honestly, like this article I found after I conducted the analysis. So it turns out like a bunch of these artists are actually deleted from Stable Diffusion 2.1. So it is possible to actually tell whether an artist style exists or not in these generative models using this sort of analysis. There is no evidence, I mean, there is no article anywhere, but however, we hypothesize that some of these guys like Ruangia, Vadim Kashin, and Tanfadi are also removed from SD 2.1 according to our analysis. Okay, so yeah, like that kind of was like a super brief pitch of this style paper. However, like I said, this is a very much an underexplored direction, and there is so much that can be done because there are like lawsuits and where artists are claiming like these models are memorizing their style. However, like again, it's a very subjective thing. Like artists might say like your style is there. However, a lay human might say like, okay, no, that's not your style. So we need to approach this problem in a little bit more scientific fashion. And I feel like our paper took like a first step towards that direction. And these are few of the potential directions I can see for this paper. First of all, I feel like dataset creation itself, a dataset can be further cleaned up, and we can further improve the training. We haven't done like an exhaustive analysis of like the training paradigms, and that could be like a good problem to study. And similarly, this is a very important point. Like our style definition right now is a little bit flawed. We assume certain keywords or certain artists kind of represent a similar style. However, there are some artists whose style has changed over time. Like if you see early paintings of Picasso and later paintings, they look quite different. So this definition itself is not quite good. Maybe we can kind of like come up with better definitions of style. And similarly, in this paper, we were studying mostly the transfer of style in simpler prompts. However, this could itself be like a big problem where the prompt could be like really long, which consists of multiple artists, and can we actually disentangle, like in fact, like for the generated image, whose style did it actually capture? Like maybe some of these keywords are just useless, they're just there, and that particular artist style might not even be present in the image. So it's a slightly complicated problem, but however it's an interesting problem and a potential direction that can be studied. Okay, so yeah, these are a few of the papers, and feel free to check out my website. All of them are listed there. And so that concludes my presentation. Thank you so much for sticking around, even though I'm like 20 minutes late. And this is my website, and or you can find me on Twitter too. So if you have any questions, feel free to reach out to me, or feel free to unmute yourself and ask here. Yeah, thank you.
I have a question.
Mhm,
It might be a little bit unrelated, but out of all the diffusion models I have used, I found that ideogram
mhm.
works best in case of like aesthetics for me for a prompt and a generated image. But I haven't seen like any analysis or evaluation that is done on ideogram.
Mhm.
Like I think it's been there for quite a while, but like not a lot of analysis has been done on ideogram. I think a lot of lawsuits that have been on stable diffusion, they can be done on ideogram as well.
I mean, I feel like ideogram is actually not as big as, first of all, it's a paid model, right? Not a lot of people use it. I feel like out of paid models, like Midjourney is quite famous, and yeah, Midjourney is part of a bunch of lawsuits. But yeah, I feel one reason could be because ideogram is, first of all, like not too big, and not many people are aware of it. It's mostly known to very, very tech people who are involved in like this sort of research, in my opinion. That could be the reason. Again, like even I don't know too much about ideogram other than the fact that it generates text well. That could be because of the way they built a diffusion model. I mean, pixel space diffusion tends to build text a little bit better, or maybe it could be conditioning to the text encoder makes a difference too. So, um, okay, yeah, that's what I think is happening, but I could be wrong.
Yeah, they have like a free version as well, so like anyone
Oh,
can generate a few images per day or something like that. But the
okay, okay.
quality I find it very better as compared
Hmm.
to Stable Diffusion or Midjourney.
Oh, you think it's better than Midjourney? Okay,
Yeah.
okay. I did not know that. Okay, cool. Maybe I should check it out. Yeah. Um, okay, I mean, I just want to say it here, if any of you guys are interested in doing a follow-up research, or if you have any ideas you want to bounce around, I'm happy to mentor somebody, or collaborate. Yeah, definitely reach out to me.
If you don't
Cool.
have any other question, I think we can end the session.
Okay, sounds good.
Yeah. Thank you very much.
All right, thank you. See you guys.